Hello everyone, Kodongwane, the native god here. On this video, we'll be looking at a problem based on relative velocity, right? Now, problems based on relative velocity can be solved using one of two methods, right? The one method is the method of components, right? So method of components, which is the one that we're going to be using for this video specifically, right? And the second method is the vector diagram method, also known as the parallelogram method, right? Now, I'm going to be using both methods in solving the problem we are looking at currently. For this video though, for this video specifically, I'll be using the method of components, right? In the video that follows after this one, right, in the playlist, I'll be solving the same problem using the parallelogram method, right? Because in engineering science, kinematics, right, it is important when having to do or when having to solve problems based on relative velocity and resulting velocity that you are familiar with both methods. So the method of components as well as the parallelogram method or vector diagram method, right? Right. Now, for this video though, like I said, this problem is based on relative velocity, right? So I'm going to take you through how we solve any problem based on relative velocity using the method of components, right? Right, let's get started. Now, with relative velocity, this is what you look out for, right? This is, or these are the most important things you need to look out for, right? They will either, in fact, yeah, these are the only things that you need to look out for. Once you've identified the things I'm about to mention, right, you essentially are good to go, right? Now, with relative velocity, what we are doing or what we are trying to do essentially is to compare the velocities of two objects, right? You'll be given two objects or however many objects, right? Can be three, can be four, but in whatever question that you need to determine, right, you will be essentially looking at just two objects, right? So with relative velocity, what you are trying to determine is the velocity of one object relative to another, or the velocity of one object compared to another, or in reference to another, or in respect to another, right? Now, you are given two objects, right? Like for instance, if you look at this problem, it reads as follows. A fighter plane Q flies at 250 kilometers per hour east, while the velocity of fighter plane P is 210 kilometers per hour west, 53 degrees south, right? As you can see here, we have two objects, right? You have object Q and object P, right? We've been given the magnitude of their velocities as well as the direction thereof, right? Now, once you've identified how many objects you are looking at, right? In this case, it is just two objects, right? You then look at the question. The question is determine the velocity of fighter plane P relative to Q, right? Now, with relative velocity, this is the most important thing to identify, right? You have to identify of the two objects, right? Which one are we going to take as the object and which one do we take as the frame of reference, right? Because like I said, with relative velocity, essentially what we are doing is we are comparing the velocity of one object relative to another, right? So the velocity that you want to determine, right, or the velocity of the object that you want to determine, that object is the one you take as the object. And the one it is relative to, right, that's the one you take as the frame of reference, right? So how you determine this will be based on the question, right? Because if you look at the statement, right, in the statement, you're just told of two objects. You are given the magnitude of their velocities as well as their direction, right? But it is in the question where you are able to establish which of the two is the object and which one is the frame of reference, right? Now, if you look at the question is determine the velocity of fighter plane P, right? So how this is denoted, right? The first letter represents the object, the second letter represents the frame of reference. So essentially, when they say determine the velocity of fighter plane P, it means they want you to determine the velocity of P, right? Relative to what? Relative to the velocity of Q, right? So because they want us to determine the velocity of P, it means object P, we are going to take as the object, and object Q, we are going to take as the frame of reference, right? Now, this could have also been denoted as follows. They also could have said VP relative to Q, right? So this can be denoted in one of two ways, either this way or this way, right? Either way, you look at the first letter, right? The first letter being P means that the object here is P and the frame of reference is Q, right? Very important that you identify which of the two is the object and which of the two is the frame of reference. Why is that important? Right. Now, in having to draw the vectors on your Cartesian plane, right? Because with relative velocity as well as resulting velocity, it is important that you draw your vectors on the Cartesian plane, right? So here's my Cartesian plane here, right? The reason why it is important to identify which of the two is the object and which is the frame of reference is because the one that you've identified as the object, right? When having to draw it on the Cartesian plane, you are going to draw it in a direction that is the same as the one that you've been given, right? If you didn't get that, pause the video, rewind it a bit, and listen to it again, right? Anyway, I'm going to say it again, right? The reason why it is important to identify which of the two is the object and which one is the frame of reference, right, is so that once you've established your object or which one is the object you are going to draw on the Cartesian plane, or you're going to represent on the Cartesian plane in a direction that is the same as the one that you've been given, right? And then the one that you've identified as the frame of reference, you are going to draw on you're going to represent on the Cartesian plane in a direction that is opposite the one that you've been given. Now, what does this mean? Now, for instance, here we have established that P is the object. So P we are going to draw on the Cartesian plane in a direction that is the same as the one that we've been given. Object P, right? Plane P, they said, is 210 kilometers per hour in a direction west, 53 degrees south, right? Now, because we've identified P, right, P as the object, it means we're going to draw it in the same direction as the one that's been given. The direction that's been given for object P is west, 53 degrees south, right? So meaning this angle, right? How we look at the direction of each vector is the direction, right? If you look at the angle, right, the direction before the angle is where the angle is a reference from, right? So meaning if the direction is such that it is on the x-axis, it means this angle is referenced from the x-axis, right? And then the direction thereafter, right, will be essentially the direction of where this vector is headed, right? So meaning if you look at this direction here, right, the direction before the angle is west. West is on the x-axis, meaning the 53 degrees is referenced from the x-axis, right? And then the direction that follows is south, meaning that this vector is headed essentially south, right? So if you look at in terms of which quadrant is this vector, right, it's west, 53 degrees south, it means it is on the third quadrant, right? So this angle being referenced from the x-axis, right, it means this is going west, right, 53 degrees, essentially this is what it means. So this is going west, right? If you can put it like this, it is going west, right, 53 degrees south, right? So we are headed south. It's going west, but 53 degrees south, right? So 53 degrees, say, is something that's approximately there, right? Right. With using the method of components, you don't necessarily have to be accurate, right? Because we won't be needing, or we won't be using the what is this, the parallelogram, or we won't be using the the vector diagram in determining in which direction the resulting velocity or the resulting velocity is going to be headed, right? So this angle we've established is 53 degrees, right? So this is headed in that direction, right? So again, object P we've identified as the object, hence the object you draw in a direction that is the same as the one we've been given, right? So this is VP, right? We can call this VP, and VP is 210 kilometers per hour, right? Right. Now we look at the frame of reference, right? The frame of reference for this problem is Q. So Q on the Cartesian plane, we are going to draw in a direction that is opposite the one that's been given, right? Now, if you look at Q, Q is headed east, right? But because for this problem, it is, or we've identified it as the frame of reference, we are going to draw it in a direction that is opposite the one that's been given, right? So the one that's been given is east, right? So we are going to draw it going in a direction west, right? Opposite of east is west. So it is headed in that direction, right? And this here is VQ. So VQ. So this here is VQ, right? So again, with relative velocity, this is the most important step, right? Identifying which of the two objects is the object and which one is the frame of reference. The reason for that is the object you draw on the Cartesian plane in the same direction as given, right? The frame of reference you draw in a direction that is opposite the one that's been given, right? Very important. Right. Now, how do we write down, or how do we denote our velocities, right? Once we've identified that direction, right? Because we are using the method of components, right? Because we're using the method of components, if your vectors are such that they are oblique vectors, right? Oblique vectors, because in using the method of components, we have to apply conditions of equilibrium, right? In applying conditions of equilibrium, all your vectors must be such that they are parallel to the Cartesian plane, right? Meaning that in applying conditions of equilibrium, right, we have to make sure that the vectors that we are using either are parallel to the y-axis or are parallel to the x-axis, right? If your vectors that you have are such that they are oblique, right, we have to then resolve them into their components, right? So for instance, if you look at this vector, right, for the velocity of plane P, it is an oblique vector. Hence, in applying conditions of equilibrium, we can't use it as it is, right? Hence, we have to resolve it into its components. In resolving it into its components, right, their components, or the components thereof, will then align or will be parallel with either the x-axis or the y-axis, right? So the y component of vector VP will be parallel with the y-axis, and the x component will be parallel to the x-axis. Hence, we'll be able to use that in applying conditions of equilibrium, right? Now let's resolve this, right? To resolve this into its components, right? It's going to have a x component as well as a y component, right? So we resolve it into its components, right? Now, at this point, you should be able to know how to resolve an oblique vector, right? But just in case you've forgotten, how we resolve an oblique vector is right, you have this vector going in this direction, right? Its components must be such that it is going towards the same direction, right? So meaning the x component must be such that it is headed towards this direction, right? So for the x component to be headed towards this direction, it means it has to go in that direction, right? Similarly with the y component, right? The y component must also be such that it is headed towards this direction. Hence, it is going to be headed in that direction. Or another way you can look at it is, right, in resolving an oblique vector into its components, right, you then essentially have three vectors. So you have the oblique vector and its components, right? If you look at this point here, this point is essentially the point of intersection, right? And this being the point of intersection, the direction of each vector must be such that it is going away from this point, right? It must be such that it is going away from this point. Hence, you see, what is this? Hence, you see each of the vectors going away from the point of intersection, right? Right. So we're going to have the component of VP in the y direction. So this we name as VPY, right? So this will be VPY, and VPY will be, now this is headed south, right? And remember, in using the Cartesian plane as direction, right, north we take as positive, east we take as positive, but west we take as negative, and south we take as negative. So seeing that this is headed south, it means this will take as negative. So this is negative 210, right? 210, what is this? Sine 53, right? So here's another thing I forgot to mention, that in having to resolve an oblique vector into its components, you must make sure that the angle you are using is referenced from the x-axis, right? Why is that important? That's important so that the y component of that vector is in terms of sine and the x component is in terms of cos, right? So for the y component of an oblique vector to be in terms of sine, the angle you are using must be such that it is referenced from the x-axis, right? So always make sure that your angles, right, of your oblique vectors are such that they are referenced from the x-axis. So meaning that had we been given a direction that is referenced from the y-axis, we would then work out the angle from the x-axis and use that one, right? Now for this case, it is very simple because the direction of this vector that we were given, right, was such that the angle was referenced from west. West is on the x-axis, meaning this angle is referenced from the x-axis, right? Right, then we have the x component of VPY, right? X component of VPY, so of VP, so the x component, VPX, is equal to, now if you look at the x component, it is headed west, hence we're going to take it as negative. So this will be negative 210 cos 53, right? So both components, right, if you look at the x component, we're able to use cos because the angle that we are using is referenced from the x-axis, and the y component of VP we're able to use or to represent in terms of sine because the angle we are using is a reference from the y-axis, right? Right, so that is VP, right? Now we'll be able to use the components of VP, right? This component is parallel to the x-axis, this component is parallel to the y-axis, hence we'll be able to use these components in applying conditions of equilibrium, right? Now when looking at VQ, right, VQ, right, is already parallel to the x-axis, right? So because we're using the method of components, right, we are going to take this vector of Q as its component, right? So meaning that instead of just naming this VQ, we are going to name it VQX, right? And VQX is equal to, now this is headed west, so we are going to take this as being negative, so this will be negative 250, right? So again, if the vector you've been given, right, is such that it is parallel to either of the axes, then you take that vector as its component when using the method of components, right? Right. Now that we've established which vector is, or which object we are taking as the object and which one we are taking as the frame of reference, and we've represented all the vectors on the Cartesian plane, now we can apply conditions of equilibrium to essentially solve for what we are looking for, right? Now, what are we looking for? We are looking for the velocity of P relative to Q, right? Now, this here, the velocity of P relative to Q is essentially the resultant, right? So this here, right, is the resultant of the vectors of object P, or the components of object P and Q, right? So meaning what? In applying conditions of equilibrium, right, you are first going to determine the the components of the resultant, right, in terms of the sum of velocities in the y direction as well as sum of velocities in the x direction, and then use the what is the thing called, Pythagoras, right, in determining the resultant being exactly what we are looking for, right? So what we are looking for is the velocity of P relative to Q. This here is essentially the resultant of both these vectors, right? Hence, seeing that we're using the method of components, we are going to apply conditions of equilibrium, right, by first determining the components of this resultant, right? So the component of VPQ in the x direction as well as the component of VPQ in the y direction, right? So in doing that, say sum of VPQ in the x direction is equal to, now we look at the components, right, as per our Cartesian plane, the components in the x direction, right, starting with P, right, starting with the component of P in the x direction, right, seeing that we're looking for P, right, relative to Q, right? So the component of P in the x direction we've denoted as VPX plus VQX, right? It is important to write this down, right, for context, right? So this is equal to VPQ is negative 210, so this is negative 210 cos 53, right, plus VQX, which is equal to negative 250, right? So this here is negative 250, right? Now, if you punch this in your calculators, we are going to get negative 376, 381, and this here is in kilometers per hour, right? Now, this is negative, right? Now remember, there is no such thing as a negative vector, right? The sign, right, tells us the direction of the vector, right? So seeing that this vector is in the x direction and it's negative, right, that tells us that this is going west. So this essentially is equal to 376,381 kilometers per hour, right, going west, right? Very important that you do not leave your answers as negative. Again, there is no such thing as a negative vector, right? That is just for maths purposes, right? It is important that once you've determined the magnitude, right, based on the sign here, you then tell us the direction of the vector, right? So seeing that this one is negative, it's in the x direction, it then means that it is going west, right? Now, this here, the sum of VPQ in the x direction, that's the x component of the resultant being VPQ, which is what we are looking for, right? Now we are going to calculate the component of VPQ in the y direction. That one we denote as the sum of VPQ in the y direction, right? So this will be equal to VP in the y direction plus VQ in the y direction, right? And this is equal to VP in the y direction is negative 210 sine 53, right, plus, now there is no component of VQ in the y direction, so meaning it is approximately equal to 0, so plus 0 there, right? And if you punch this in your calculators, right, we are going to get negative 167, right, comma 713. So this is in kilometers per hour, right? Again, the sign here, right, tells us of the direction of this component. That's the direction of this component. So saying that the component is a y component, right, because it's negative, it then means that it is headed south. So you then say here, this is actually 167,713 kilometers per hour going south, right? The direction of the components is important, right, when having to determine the resultant, or when having to determine the velocity that we are looking for, right? So in relative velocity, right, when having to determine the velocity of one object relative to another, that velocity will always be the resultant, right? And the direction of its components will essentially give us an idea of which quadrant the resultant, right, is going to be headed, right? Right. Now, before calculating or before using Pythagoras to determine the velocity of P relative to Q, right, so let's first calculate the angle of the direction, right? Now, this is my advice to you, right? To always, the angle that you must use, right, must always be referenced from the x-axis, right? It makes things easier, right, if the angle you're going to be using is always going to be referenced from the x-axis, right? And as such, in having to calculate the angle of direction, right, of the resultant here, right, you simply use, right, tan theta, right? So theta would be the angle, right? Now, the right hand side of this equation, right, because our theta is referenced from the x-axis, right, because this is a reference from the x-axis, the right hand side will be the sum of VPQ in the y direction divided by the sum of VPQ in the x direction, right? If the angle is a reference from the x-axis, right, this is what you use, right? That way, you know that you will never have to have this the other way around, meaning you will never have, right, as a numerator, you will never have the sum of VPQ in the x direction divided by the sum of VPQ in the y direction, right? Again, reference your angles, right? Always use the angle that is referenced from the x-axis. So because our angle is referenced from the x-axis, this is how your right hand side is going to be, right? This is how your right hand side will always, or is always going to be, right? Even if you look at, right, for engineering science, if you look at the formula sheet, right, tan theta, right, this is what this is how they have tan theta, right? The numerator is the y component and the denominator is the x component, right? That essentially means that this angle is referenced from the x-axis. So whichever angle that we get here will be referenced from the x-axis, right? So to get the angle, right, we then have to calculate the arctan, right, of the sum of VPQ in the y direction, right? In the y direction, we have 167. So this is 167, 713 divided by, right, VPQ in the x direction, which we got 376. So this is 376, right, comma 381, right? Notice how I didn't use, right, the negative sign here, right? That is because once you've established the direction and you've written the direction, right, there is no need for you, right, once you've established the direction, right, there is no need for you to write down the negative right here, right? Now if you calculate this, now if you punch this in your calculators, we are going to get 24,017 degrees, right? Now we get 24,017 degrees, right? This, right, is referenced from the x-axis. Right, now we can calculate VPQ using Pythagoras. Right, VPQ, right, remember, is the resultant, which is what we are looking for. Right, using Pythagoras, this will be the square root of, so the square root of the sum of VPQ in the x direction squared plus the sum of VPQY, right, all squared. Right, right, now all we need to do here is substitute. Now all we need to do is substitute. Right, right, so sum of VPQ in the x direction is the 376,381 all squared plus sum of VPQ in the y direction, which is 167,713 squared. Right, now if you punch that in your calculators, we are going to get 412,056. Remember, this is in kilometers per hour. Right, now how we write down, right, the resultant, right, you have to write its magnitude as well as its direction, right, which we've already essentially established. Right, so we have the magnitude. Right, remember, this angle is referenced from the x-axis. As far as the x-axis, right, which we get from the x component of the resultant, as far as our x-axis, the x-axis are headed west. Right, so our angle reference from the x-axis means that, seeing that the component of VQ in the x direction is headed west, it means our angle is referenced from west. Our angle is 24,017 degrees. Where is it going? We then look at the y-axis. The y-axis, or the component of the resultant in the y direction, is going south. So we have south on this side. Right, right, and that is how you determine, right, the velocity of one object relative to another using the method of components. Right, so meaning that had the angle that we used, or had we used an angle that is referenced from the y-axis, it will then mean that VPQ is equal to 412,056 kilometers per hour. Right, direction, if the angle that you use, right, now this is just for intersect, if the angle that you use is referenced from the y-axis, it means the y-axis we've already established is south, so you'd have south first here. Right, and then as far as the angle, right, remember that if the angle was referenced from the y-axis, right, to get that angle, you simply say 90 minus the 24,017, right, and you should get the angle, and the angle is going to be 65,983 degrees. Headed where? Headed west. Right, so if you are comfortable with referencing your angles from the y-axis, this is what you should have, or this is what you would have. Right, either way, right, these directions, right, tell us in which quadrant the the resultant velocity, right, for these vectors is going to be. Right, and looking at the fact that we have south and west, right, south and west is essentially in the third quadrant. Right, right, either way though, this is how you determine the relative velocity, right, or this is how you solve problems based on relative velocity using the method of components. Right, hopefully this helps. See you on the next video.